In this video, we'll be looking at what is often called the linearity of differentiation, which means the simple way in which it responds to functions being added or subtracted, or being scaled by a constant number. So first, let's have a look at addition and subtraction. Now, differentiation measures the small changes to the function value in response to some push in the input. So let's just say that both these numbers 8 and 5 have changed by some amount. So now it's 8.02 and 5.03. Then the resulting number, when you add these two things together, would be 13.05. And clearly the total extra amount of 0.05 came from the change of 0.02 adding with the change of 0.03. That is to say, the total change in the value is equal to the sum of the individual changes. Now, all of this might seem awfully obvious, but there's something really nice about differentiation we can get from this, which is if your function, like this one, is made of a bunch of separate terms, just adding or subtracting together, then when you go to measure dy dx, which is really measuring a total change in y value in response to a small push to the x value, well, we can apply the same logic to this function here. And we can just take the sum of the individual changes, meaning we just differentiate x squared, giving 2x, and then we add this separately to the derivative of x cubed. Remember, the 3 hops down and the cube drops to a square. So if you see any addition or subtraction, just do each one separately, then add or subtract the results at the end. Now note, this doesn't work for multiplication. If we tried doing the same thing with 8 times 5 being 40, we could again see what happens when we change the 8 to 8.02 and 5 to 5.03, and it turns out the answer is 40.3406. But if you just separate out the changes of 0.02 and 0.03 and just multiply them, you actually get 0.0006, which is very different from the actual total change of 0.3406. So it's not so simple for products. Okay, if you get two functions multiplying together, you cannot do each one separately, then multiply. That doesn't work. Okay, how exactly we handle that case will be in a future video. One thing we can salvage though is when we multiply by a constant number. So not two different functions of x, but when we multiply just by a constant number. So here, doubling 5 is obviously 10. But if we just push the 5 across, say by 0.03 again, then the answer is 10.06. And it is true that this total change of 0.06 came from simply doubling the change of 0.03. So we can say constant multiples apply directly to changes like that. And all that means in the context of differentiation is that when we measure the rate of change here, we can once again apply this logic, meaning this constant multiple of 4 just multiplies directly with the derivative of x to the 9. So drop the 9, decrease x9 to x8. So the rhythm you'll get used to very soon is to just leave constant multiples alone. They just tag along for the ride, but otherwise don't do anything. So finally, the 9 multiplies the 4, giving 36, then finish with the x to the 8. Okay, so let's do one final example combining a lot of what we've seen so far. We're trying to differentiate this beast here. So now first with the bracket, remember we can't differentiate products separately. So our best bet here is to just expand the bracket first. So we have x cubed times 2x is 2x to the 4. Then x cubed times 5x8 is 5x11. Then the plus 6x plus 1 just join in. So now we can think about differentiating all of this. Because it's just a bunch of separate terms, adding and subtracting each other, we can do each of them separately. So, 2x to the 4 first. Remember, the constant multiple of 2 just stays. So the 4 hops down to join it, giving 4 times 2, which is 8. Then we minus 1 to the power, giving x cubed. Next, the negative 5x to the 11. The constant minus 5 stays put, so the 11 hops down to join it, giving minus 5 times 11, which is minus 55. Then we minus 1 to the power, giving x 10. Then the plus 6x plus 1, which I find surprisingly confuses some people first time they see it. Maybe because it feels too simple, I don't know. But remember, dy dx is just measuring gradient, only that it now extends to working for curves and stuff. So it is still just a gradient, and hopefully we've made a big enough deal of that. So this 6x plus 1 thing is just a straight line. And you've known the gradient of this for ages, it's just the gradient of 6, right? We don't include the x for the gradient of a straight line. And in general, we can ignore any constant out here, because all the plus 1 would do here is shift the whole graph up by 1, and in general, shifting a graph up and down does nothing to its steepness, to its gradient. So any constant you add or subtract out the end like that can just go away. Okay, so that's our derivative. That's the equation that gives you the gradient of that original monster at any value of x you want. So that's all for this one. Thanks for watching. See you around.